Record. All right, so we are here for the second talk of today, which will be delivered by Bart Vandereycken, who is currently an associate professor, if I'm not mistaken, at the Université de Geneva, which is in Switzerland, even though it's French, the name of your university, of course. And Bart, he was previously at Princeton University, also spent some time at EPFL and also in Zurich, apparently, after, of course, obtaining his PhD at the most important university, Leuven, of course, here in this group. All right, so Bart is, of course, well known for his many works in, let's say, numerical linear algebra. And today he will give us a presentation about streaming tensor approximation. Bart, please.
Okay, thanks, Nick, for the very nice introduction and the invitation. Let me speak here. So I hope I will stay near the laptop so that my voice is also recorded. But I will use a pointer to point on the slide. So I'm sorry for the people online, that will not be. Okay, so this is a work I've done recently with my PhD student, Erik Voorhaar, who's Dutch, but he's also in Geneva, and together with Daniel Kresner, who is at EPFL, which is the university next to, not far from Geneva. So the Université de Genève is in French, Nick, because Switzerland has 4 official languages.
One more than Belgium.
Exactly.
That's why you went to Switzerland, though.
That's right. Now I'm trying to find a country with 5 official languages. Good. So the topic of the talk is about tensor approximation. So I'm happy to see that this funding scheme that you have set up has tensor in the name. So I hope this will be very useful for the people that are in this group. And I will talk about tensor trains, which is a particular form of low-rank tensors. I hope you have already heard about it. And we want to compute low-rank approximations of a tensor in this format of tensor trains. So that's something that's already well known, but what we do new here is that it's in the so-called streaming model. So you will see what this means along. Okay, so let's do a brief recap of low-rank approximations. So tensor trains use low-rank approximations of certain unfoldings or flattenings of the tensor. So the operation of computing a low-rank approximation of a tensor comes back all the time. You probably all know how to compute the best low-rank approximation of a matrix. It's just by using the SVD and then truncating up until the first K components. Okay. So that's all very well known, but it's quite expensive and it's not very flexible. And it's also asking for too much. So in data approximation, you want to have a good low-rank approximation if you can do that fast. If you have to pay a high price for computing the best low-rank approximation, then maybe that price is a little bit too high, and you are happy with something that is very close to the best. So one of the ways to compute good low-rank approximation faster than using the truncated SVD is by randomized techniques. So we use something which is called the randomized SVD. So this is something that has become very popular over the last 10 years. It has been around for longer, but I think there's a famous paper by Halko, Mattison, and Trop, where they analyze these randomized methods in a lot of detail, and the algorithm the basic algorithm is very simple. So you see it here. I am working with a matrix of size m by n. I would like a rank R approximation. So what do? I draw a random matrix X of size n by R. I multiply it by the matrix A on the right. I orthogonalize the columns in this matrix by a QR decomposition. And then with this Q, I can form this approximation. So you see that Q has R columns. So that's on the left. And then on the right, you have Q transpose A. This is a matrix with R rows. So you have obtained a vectored form. So there's a matrix as a multiplication of two smaller matrices. So that's usually what you want with the low rank approximation. And this will be of rank typically equal to R, or at most R certainly. So this is the HMT approximation. And that's it. This is the algorithm. So it's really like 3 lines, super simple. So it's nothing new, actually. This is just one step of subspace iteration. So if you do subspace iteration, you would do exactly this, but you would continue to iterate with A transpose A in there. And this will eventually converge to the top subspace of the top singular vectors of the matrix. Now, what's crucial here is that you stop already after one step, and you don't really care about the quality of this Q as an approximation of the top singular subspace, but you care about it as a way to get slow rank approximation. So you go directly to the goal in a way, and you care about the error of A compared to the low rank approximation. So it's a random algorithm, because here you take a random Gaussian matrix. So every time the result will be different. So you can study this with probabilistic means. And the easiest result you can have, that's actually not so difficult to prove, is about the expectation of this error. So here you have the error of the HMT methods, and here you have the error of the best approximation of rank R. And in expectation, of course, this will be bigger, but you have here a factor that you pay. And this factor is 1 plus something, and the something is not too big. So it cannot be smaller than that, but it's only slightly. So we call this a quasi-optimal error, where this, you can take it arbitrarily small. And the trick that the people realized over here is that you have to compare not to the rank R matrix, but to a rank R hat, where R hat is slightly smaller than R. So this is called oversampling of the rank. And if you do this a little bit higher, you can see here that this will be bounded. So you have to take it bigger than +1. R hat needs to be bigger than R plus 1, otherwise it's 0. But if you take it a little bit higher, then this will be a small factor and okay, so that's to prove an expectation. You can also prove about failure probabilities. What is the probability that this is higher than something? Blah, blah. And I will not talk about this, but this has been done, but this kind of works, and it's very low. It's exponentially. Okay, so this is a very good method. It's very easy to implement. You can improve it a little bit more, but I think for many cases, this is already very good. The problem in very big data, very high dimensions, is that it's a little bit too sequential. So you see here, you compute this, and then you have to do QR, which is sequential, typically a sequential algorithm like Gram-Schmidt. And then you have to project A again with Q. So you have to access A 2 times. Okay? So we would like something that is less sequential and only one pass. That means you only have to see A once, then you do some work on it, and then you throw it away. So this can be done for the low rank approximation, and this is an algorithm that goes back even further than the HMT methods by people in theoretical computer science. They have proposed this algorithm here. It comes with many names. I use the name generalized Nystrom because in the symmetric version is the Nystrom method. It's a very well-known method, very good method. In the non-symmetric version, so the name is not very standard, but the algorithm occurs in many places. So what you do here? Well, the trick is that you don't multiply A only on the right, you also multiply it on the left. You see here, Y transpose. So you draw now two sketches, two random matrices, sorry, X and Y, and then you multiply these things out, and we call them sketches. And once you have done this, you throw A away, and you form the low rank approximation in this method. So you see here that X has R columns. So this guy will have R columns. the Y has R plus L columns, so a little bit higher. L is a small number. So this guy will have R plus L rows. And then in the middle, you need something in order to fit. So you see you have again a low rank vectored form with the multiplication of 3 matrices. And those. So this dagger notation means the least square solution. So this is a rectangular matrix, so it has no inverse. So if you multiply it on the right or you multiply it on the left, you will solve an under or an overdetermined least square problem. But okay, that's easy to do. No problem.
Is there a reason to choose L different from 0?
Yes.
Okay. And
In practice and in theory.
Okay.
It's very, very important to use L, let's say 2 or higher.
Okay.
If you use L0, this will be very bad.
Okay.
So here you see the error. So this is, you need to compare this to that. Huh? So keep in mind this vector. We have it here as well, but you add. So it's slightly worse, but what you pay is again quite small, and you see here the L popping. So if L is equal to 2, you're okay. You can take L, you can take this to be L equal to R, and then you're very so this is the error that you can prove, an expectation. It's also not very complicated. And like I say, the nice thing here is that it's one pass. If you do this once, you have your sketch, then you can throw A away, and then you work on the sketches. So you can stop here if you want, or you can really work this out, this least squares problem, if you want something that only involves two groups. But this least square problem is cheap. Now, what's also very nice is that computing these sketches here, it just matrix multiplication, but it's so it's very fast in GPUs and distributed computing, but it's also linear in the input. So the input here is the matrix A. So suppose your A changes linearly, A plus B, then because this is linear and this is the most work, I can do the computation first on A, I get these sketches, then I throw A away, then some update comes for A in the form of B. I do this for B, and then because of linearity, I can just sum the sketches and I'm. So this is a very nice way of updating my approximation without going back in this. So you can update and compute the sketches along. So this is what we call streaming, the streaming model. The data comes as a stream, as a linear updating sum, and you cannot go back in history. You can only do one pass, and it's not needed for something to be linear, but it's very easy if the algorithm is. Well, I say the algorithm linear, but that's not really true. This is of course not linear in A, but the dominating cost of the algorithm computing these sketches is linear in A. I do numerical linear algebra, but of course not everything is linear what we do. So this is not linear. So you have to be careful what you mean with linear in the input, but this.
So you still have a QR?
No,
you don't.
No.
How do you solve the?
Okay, yes. No, that's not QR. It's better to use with S.
Okay.
So so you don't orthogonalize with big matrices. So you don't QR, you don't do a QR on AX. You do a SVD on the tiny R by R.
Yeah, that's smaller.
So that's much better. Oh. So this is for matrices. Now we want to do things like that for them. And there you will see it will make an even more dramatic effect about the tensor. Okay, so just one slide about tensors. I'm sorry if you have not seen this, but I hope Nick has already talked about this many times here. So if you have a matrix that is of rank R, then you can factor it as a product of two matrices that have R columns and R rows, transpose missing. Then one way to see this element-wise is in this. So these are the elements of the row and the column, and then you have a sum with an index chain. Now, if you generalize this to tensors, I think there's two big families to do that. One is with the CP decomposition, and then you have an index here that's shared over all the different C. So here you have only two Cs. With a D-ordered tensor, you have DCs. Or you can go to what's called subspace representations, and then the best known example is the matrix product state of the tensor train composition, and then you have this. So you see here there's only one J, here there's multiple J's. So J1 is connecting this, J2 is connecting that, and so on, and then the last J. Okay, so some people also present in the room like a lot the CPD composition because it is a very it has a very nice mathematical description. It has very elegant properties, very intriguing properties as well. But that also makes it very difficult to work to optimize it. So if you care only about data compression, then you don't care about the hidden latent factors in the model. You're happy with it. And in my opinion, that in the most applications that I see in, let's say, computational physics, most of the time people use this kind of decomposition because they are much nicer to work with, and they also work for what you need. Okay, so we will work with this set. So we want to have an approximation of a given tensor in this form. And you see what you need to compute here are these scores C. So these are the extensions of the matrices C1 and C2 that I've talked to you earlier about. Okay, so that's a lot of sums here, a lot of indices. So most people in this world now, they do things with diagrams. So here is a diagram of a TT. So because this is just a rule to contract certain matrices. So you see C1 is connected with C2 with the sum J1 over here, and then C2 is connected with C3 with another sum, and then so this kind of contraction rules you can also draw. So here C1 and C2 is connected, and R1 here is to say that you have R1 a sum of dimension. So this you do for all the rest. So you get here a train of and the x, the original x, is a tensor of order D, and the number of legs that you see here is the order of the tensor, and the n is the dimension of the vector space. So here you still have n1 and 2 and d, so it's representing the same thing, but here it's the general tensor, here it's in factor. So I will make use of this diagram further to illustrate you how algorithms work. So it's not only just a visual tool, it's also a nice tool to prove certain properties and to define algorithms. So, for example, the first algorithm is how to compute a low rank TT approximation of a given tensor. So this is the analog of the truncated SVD for matrices. It goes back to Ozilidets in 2011. Just a few slides to show you the similarities with the matrix space and also what we improved later on. So I give you an original tensor T. It has the order B. Then a tensor is just an array of numbers. So I can also represent it as a matrix, which is called a flattening or a matricization, where I treat this dimension as the rows, and these dimensions I all group together as the columns. Then I can do a normal truncated SVD because it's a matrix. I throw away all the small singular values, and I end up with a matrix that is of low rank, let's say K, that is given as a product of two matrices, where U1 represents all the left singular vectors. So U1 is the left singular vectors, and then the singular values and the right singular vectors I all put in the matrix T1. So that's the first step. This is just matrix approximation. Now, here I do things recursively. So what do I do here? I take T1, and I realize actually this is a tensor as well. It was a matrix before, but I can unravel it into a tensor. So then I do the same idea as here. I make it into a matrix where I take those two indices together and the rows, and then these are the columns. And then I have a U2 and then a T2 prime as the next. And from that, you can imagine how it continues. You just cut the network here, you do tensor, you do matrix approximation, And you continue until you are at the very end, and then it's finished. And you see in every step, I get U1, U2, U3, and so on. These are basically singular vectors that are reshaped into the cores that I need for my TT approximation. So there's the algorithm TT-SVD. It's the extension of the higher order SVD by Lieven, the Lathouwer for Tucker, which was invented also in Leuven, but in another department. So this is the immediate extension to TT. Quite surprisingly, this has a quasi-optimal error as well, and it's deterministic. So it's funny to note that in TT, we do not know how to compute efficiently the best approximation of a certain rank. We know it exists, but we cannot compute it. However, we can compute something which is very close to it, provably. So the constant here will be 1 over, I think, D. So that's for many practical purposes more than so in some sense this is a perfect algorithm. However, in the very large scale, again, it's not that perfect because it's not one pass. It's clear you need to access the T many times along the way sequentially. So you cannot really update it if you have some approximation for T, and then for U you can do some tricks, but you cannot really mathematically update in an equivalent way. You need to do some clever tricks. And also important, it destroys the structure in T. So if T is, for example, very sparse, it's a big tensor, but with many zeros, then what you do here already destroys the sparsity. So here you project with all these matrices, so you will mix all the entries of T, and you will get a non-sparse tensor. And you can maybe do this step once, but then you cannot do it. So sparsity is not preserved. It's not. Okay, so now you can go back to my previous slide, and you can say, but why don't you use the HMT methods? Because the HMT method was an improvement over the truncated SVD. So this has been done already. So this is an algorithm of Hüber, Schneider, and Wolf, where they very simply replaced the truncated SVDs by the TT-HMT. So it's not a groundbreaking idea. It's very simple to do. And so what you do here, you take your tensor T and you multiply it on the right by this random matrix. You get the sketch of the tensor, and then this sketch you will take a QR factor, and then this QR factor will be your new code. And then from there you can continue. So that's what they presented in their original work. We noticed actually that it's not so good to really do it in this fashion where you cut the network and continue. It's better to apply now this U1 to the original T, so that the structure in the T is preserved. So in the second step, you project with the original U1, you take a new random matrix X2, you compute this sketch, this is the P2, you do a QR, and then you continue. So if you really look at this algorithm on paper, you see it's the immediate equivalence of TT-HMT applied to the trunk. Continue after mu steps. So you see here, you can phrase this algorithm as an operation on the original T with some contractions of things you already know. Things are random, but you operate on the original T every time. So clearly it's not one pass. I need to compute T based, I need to compute certain quantities with T based on previous computed quantities, but it preserves the structure. So if T is sparse, okay, very good. It will remain sparse over the years. So that's a nice thing of this. And then you continue in stage. So what you can prove here, that's also it's quasi-optimal in expectation. You can prove it as very low failure probability, just like the HMT method for matrices. If the tensor is sparse, then you're happy because you can use Gaussian matrices, because many things will be zero in these kind of contractions. But unfortunately, it's not streamable. It's not. So now you can all guess what will come next, right? It is the extension of two-pass algorithm to the TTS. So this is what we propose in this paper here. So I gave you a long introduction also to show you how the previous algorithms are they're not very difficult, but they are not the simplest either. So the algorithm that we propose is actually very, very simple. So what you need to compute is here in one slide. So you have your tensor T. It's an ordered D tensor. So you can flatten it in many different ways. You can group the first indices and the last in D different ways. So you have D different unfoldings. And each of these unfoldings you will hit on the left and the right by random matrices X and Y. So here you see, this is the easiest one. So you see you have T here, it becomes a matrix. And these are the rows, these are the columns, and then you hit it on the left with the Y and hit it on the right with X. The same X and Y you also use for this thing, where now there's just one index. So what that means is that you will compute sketches of the tensor that are called C and omega, and you have D of them. So D of those and D of those. The sizes of these X and Y, they are written here, and they need to be different. So like the L before, you need some difference in there for theoretical and practical reasons. Okay, so that's the work that you do. Clearly, it is one pass because, I mean, there are D versions of that, but they all come in one go. At the start of the algorithm, you do all of that. You do it parallel. It's embarrassingly parallel over the D modes, of course. And also this is highly parallelizable because it's just matrix. It's a tensor contraction. So this can be very fast. Also on a GPU, it's super fast. You do this once, and then you throw T away, and then you keep these things. And with those things, you can make a network in this way. So you see here are the cores. And in the middle, we have, again, these pseudo inverses that I had before. So these are the least squares. So depending on your needs, you might stop here. So this is a data sparse construction of a representation of the original tensor T. If you really want a TT like this, well, then you have to multiply this out to the right or to the left, depending on this. But that's a small cost. This is a small least. So this is for free. This you need to work, but it's very cheap. Okay, good. Right, and so this is the algorithm. Let's skip this. This is really, yeah. So hey, let's skip the main idea. I just give you the algorithm. I think that's fine. So some of the properties, it's very easy to implement once you know how to compute a tensor contraction in TT. Then you can implement this. And this is really the basic computational ingredient in tensor computation. So this should be fine. And you can clearly just do it in a distributed setting because all these contractions are independent. It is streamable because it's linear in every sketch in the data. Every sketch is linear in the input tensor, and you only need to touch the tensor once in the intro. Once we started to work on this, we noticed that there's a recent paper by Daals and many other co-authors. And we figured out that actually this algorithm is mathematically equivalent to one of the algorithms that they propose, but you need to, you need to work it out. So the eventual approximation is equivalent, but not the algorithm. And in particular, their algorithm, what they propose, is not streamable. They do too many steps intermediately in order so that they lose the streamability. And we think this is one of the nice properties of this algorithm. So it's a pity they, in a way, did not realize that their algorithm could also be streamable. And furthermore, they have no error analysis of the algorithm, but I will come back to that in the next. So let me give you a very simple numerical experiment to convince you that also in practice it works quite well. So here is the Hilbert tensor. of dimension, I forgot, it's 4 or 5. So this is a tensor that you can form explicitly, and it has exponentially decaying singular values across all the flattenings. So that means it has a very good low rank approximation. Here you see the TT rank. They're the same in all the modes. So it's a vector, of course, but here it's the same across all the modes. And you see that this is the error in blue of TT-SVD. So this is the algorithm that in some way is the best approximation, but it's not really, but we treat it as the best. And then here in the colors, so the 4 different colors for every rank, you see 4 different algorithms. So I explained to you the TT-HMT and the STTA. So this is in sort of yellow, mustard maybe. This is in what is this? Some kind of fancy red. And you see, well, you can see first of all that all these error bars are in a way similar. So it's a random algorithm, so of course they will not be spot on the same, but you see that they are not too big and they are comparable certainly. So TT-HMT compared to STTA, you cannot really say it's better. It's maybe slightly better, but the difference is not dramatic. Whereas with STTA, it is a streamable algorithm, whereas the TT-HMT is not streamable. And the cost is really, I mean, it depends how you compare things, but they have comparable costs. Now, this is for Gaussian DRMs. So this is when your matrix X that I talked to you about, that you need to multiply with, is just a random Gaussian matrix with all entries independent. That's clearly an unstructured matrix by definition, and it's very good in theory. And you can prove things for such a Gaussian matrix. If the tensor that you want to approximate is not very sparse, then you cannot use a Gaussian DRM because it's too costly. So then people have used structured random matrices, and something that works very well here is something that is structured as a TT as well. You contract with a TT that has random cores. This has a lot lower randomness, and there is literally no theory for that. It's a very big open problem. It's also very complicated. But of course, you can implement it and see what you get. And you can see here what you get is very good. There's really no difference between this TT-DRM and the Gaussian DRM. And this is, for me, very surprising. I would have thought that is some small price to pay, but even here you see that there's nothing. So just a few words about the theory. So what we can prove is an error bound in expectation. So this is very similar to the bounds that I gave you for the HMT and the generalized Nystrom. So you have here the expected value of the approximation T tilde with the original T. You compare it to the best rank R hat approximation. And the trick is again to take R hat a little bit smaller than the ranks that you used in your matrices. Huh? So you don't compare the core of size R directly with the rank R, but of R minus 2, let's say. And then here you have some constants, which will tell you how much you are away from the best approximation. And before in matrices, this was 1 plus epsilon. So here it's a little bit similar. It's 1 plus square root epsilon if you want. But what's not so nice here is that you get here a product of eventually d minus 1. So you get here 1 plus epsilon to the power d. That's, I mean, every c is okay, but you have d, and you have a product. So, so in some sense, this is an exponential dependence on the dimension d, even though you can get this quite small. But then you have to take the oversampling quite big. But okay, that's the best we could do. The proof is well, it's I would say 2 pages, but not completely trivial. So I will skip this here. But yeah, but okay. So this is what in the end we were quite happy with this. And as you could see, the practical performance is much better than T. So there's no exponential dependence on D. We're looking at the numerical expression. Okay. Yeah. So this is just to say that okay. You have to compare this with this. So this is C. Let's look at this. This is omega. I have T contracted on the left and the right with big random matrices that are unstructured. If you do it structured, you will do it like this. This is your original T, and then this would be your X, and this would be your Y. So you have an X and Y that is structured as TT, and then people that are familiar with those things will realize, okay, this you can compute very quickly. This is a tensor. So here's an experiment where we take an approximation of a linear combination of two structures. So because the algorithm is linear in the dominating cost, it's very easy to program it for a linear combination of different structures. You just have to compute once a way to do a fast to do SCTA with a TT. You do SCTA with a CP, SCTA with a sparse. So you do that once, and then because of linearity, you just cut it into sum. You do it once for every structure, and you sum it up. So here's just an example of a TT with a sparse tensor, and then here you see the numerical behavior. You see it of HMT, and you see SCTA, and here you see that HMT is slightly better than this. But in the end, it's still going down exponentially. You have to. Okay, here is the dependence on the order. So here is the order of the tensor. Rick went a bit overboard with the dimension. He went into dimension 8,000. Just to see if there is some dependence on this D. So in the theory, you have an exponential dependence. So with 8,000, I think you can see the exponential dependence quite quickly in an experiment. But here you see the error kind of flattens off for both algorithms. So this is provably not dependent on the dimension. This we cannot prove, but you see it has the same scaling. So empirically for this tensor, there's no dependence. It's a nice open problem how to prove this. Okay, and then finally the timing. So that's my last slide. So here we compared the time it takes to do a TT approximation using TT-HMT and with ST. Okay, so we did it on a CPU with many cores. This is all shared memory, so nothing too fancy. But if you have one of those monstrous machines with many cores, you can just throw it on there and let it run. And then here you see the time it takes. In this mustard yellow color, you see the STTA, and you see importantly the slope is different compared to the original agent. So you see it is also here faster to calculate. Also here you see with respect to the rank, this has a slower slope than the HMT now. So you can hope that if you even go to bigger dimensions, to many more cores, this effect will become more true. Okay, so and that's it. So I gave you a streamable algorithm for TT approximation. It works quite well. It's very easy to implement. I would say it works surprisingly well. You can have structured DRMs as well if you don't care about theory. If you have a sparse one, you can do provably Gaussian DRMs. It scales very well. There is some nice code available. So if you really want to play with this, you can have a look. Rick did a very nice job in documenting his code even. And the paper was put on archive, I think. Okay, thanks.
Right, do we have any questions here? And I will move over here. Do we have any questions online? Okay, Wouter.
Yeah, start of the presentation. I think
Maybe I will repeat the question for online.
yeah, you said that's typically setting out two words well in practice. But until you see how the theory is, because
So wait a second.
I'm sorry. You said that in practice you get L to 2 and you get the approximation for the approximation. But in the theory here, if I understand correctly, you multiply a theory's error bound by a factor of 1 plus R in that case. R can be then under that. So does this mean that the theoretical boundary is way to lose or something?
So let me repeat the question for online. The question is about the value of L. It was previously said that L equals 2 is in practice or could be used so that in the error bound in the middle over here, ta-da, you see that everything is well defined. But in practice, of course, if L would be equal to 2, this number here would be R plus 1. Is this not large? But question mark, and is maybe the bound loose in practice?
Yes. So okay. Okay, what is large? So 1 plus R, maybe even theoretically for some people is okay, because also you take a square root of it. But okay. So maybe indeed this is not good enough for you theoretically. Well, then you take L equal to R. If L is equal to R, I think you agree there will be no problem here.
That's more interesting.
Yes.
I was surprised that if you have, let's say, 100 on one side, you only take a couple extra points.
Yes, but if you really go to very large computations, then taking L equal to R, this is kind of painful. Because the cost of these things, well, it will be R plus L times R squared here. Yeah, so that's still linear, but sometimes there's a quadratic term over there, so then it's 4 times more expensive. So then it becomes tricky. So probably also the bound is loose here. So certainly for many tensors. So if I take the example here you see, you see plus 3 times 2. So the plus 3 is with L equal to 3. Times 2 is where L is equal to R. So what do we see here? We see in green the cost of the times 2. Yeah, that's clearly more expensive than the plus 3. So this is the price you pay of having something that is theoretically more pleasing. With respect to the error, well, I didn't really plot this here, but you see in both of these things go down. So there's not something weird going on if you, for this tensor, take plus 3.
So if you are trying to optimize error versus computation time, plus 3 works well.
If you have I'm pretty sure this works well if you have a tensor for which the singular values decay exponentially. If you have a tensor for which singular values decay very slowly, then it's better to use the times 3. So this kind of statements also appear in the matrix case. So in the matrix case with the HMT method, you have the same questions. So in the HMT method, you also have you have here R hat and R. So there's also some oversampling going on over here. So also there you have similar behaviors. And I didn't investigate it specifically for tensors, but for matrices, you see clearly this kind of different behavior. If you have exponential decay, you can take L a linear term plus an additive term. If it's not exponentially decaying, it's better to take it equal to R, let's say, to be safe.
Another question too, that's fine.
Sure, I'll repeat the question for the people online.
Yeah, then on side, I think around 11. What about your main algorithm? And the way the structure was preserved. Yeah, I'm talking about figure size, but it wasn't very clear how you can. Not very clear how you can compute the basis, the factor matrices, without applying transformation to the core. So is this similar to what if you would compare, let's say, an HSD algorithm to an SHSD algorithm, where in one case you compute the basis based on the original data or all the actions, and in the other case you first apply the transformation and then you compute the basis, or is there
I didn't understand the algorithm. These two algorithms.
You have the TOC4Deep from the Lotta, you know.
Yes.
Yeah, and then sequential variants by and others. Used in both there, you transform each time you obtain a factor, you transform that dimension already done most of it.
Yes. Okay. Yeah. Okay.
Which is actually goes to what the SPD already does. So you go back then there and
Okay. I think I understood your question. So
maybe you can recapitulate the question in that case.
sorry.
But now you can change the question to your liking.
Yes. So okay, yeah. Let me try to be serious for once. So the question is, so I mentioned a few times that you can preserve structure in the T. So in the higher order SVD for Tucker, you have a similar question in the sense that for the original higher order SVD of the Lathauer, you can preserve structure because you do unfoldings on every mode, and then you multiply later. But in the sequentially truncated of Nick, you reduce the size of the tensor along the way, and then you lose structure in the T. Yes. So that is what's happening here. So here, this is the sequentially truncated of Nick applied for T. So here you cut it and you transform it and so on and so on. So here you lose it. You can also make this work in the original higher order SVD version of the Lathauer, but nobody does this because it becomes very expensive. But you could do this if you want. Here in the TT-HMT, how I presented it is preserving the structure because you don't multiply this out immediately. You multiply it out when you need it. And if the T is sparse, this is just a big sum where many entries are 0. So then you can do that. However, if you have all those and you multiply them out, then you have a big tensor T here that you still need to multiply with an X later, and that's very complicated to program efficiently. But in our case,
it's okay. I was curious if the algorithm was similar to that. Different, but I don't think.
No. Our algorithm is different in the sense that this looks the same in a way. This is something on the left, this is something on the right. But maybe the crucial thing is that the something on the left and the right are already known at the start of the algorithm. So there's no sequential pattern.
Yes.
So this is what I said, embarrassingly parallel. So at the start, you draw all these random matrices around n in MATLAB. This you do once and it's finished. And then you do all these computations. And then later you do stuff with those things. But at the start, there's nothing sequential. All the other algorithms are sequential in nature. You transform the tensor and then you do stuff with it. Here you don't change it. You do this at the beginning and it's finished. Okay.
One last question. That's also fun.
Sure.
About the nature of your data. The whole application of this setup is about data which then updates over time with smaller structured data too, because it would make sense. But I then thinking about some sparse data sets where more sparse entries are added over time.
Okay, so the question is, what kind of applications do you have in mind where this tensor is updated linearly along the time? Is it like sparse data where entries get filled in? And here I have to say I have one concrete example in mind, but it has not been worked out. So so yeah, what you propose, some sparse data of observations that's every day gets added by new observations because people online give you some ratings or whatever. That's indeed something that would fit. But I have no concrete plan of working that out, let's say. But that's yeah, this is the streaming model. I mean, it's not so hard to convince yourself of some applications. Whether they will work in practice, whether they will be competitive, that's a different thing. But somebody needs to work this out.
Do we have other questions? Other questions online? No questions online. I have one question actually. So do you know this work by Yassine Niyet, I think, where they basically say, so the way that you show the TTSVD algorithm here, it basically is like a left to right version of computing the TTSVD. So you separate one and then you take the next two and so on and so forth. So ultimately, if you think about H Tucker, it constructs a tree where the N1 would be at the top, basically. And then you go down to the right. And so what this paper by Yassine did, they said, okay, well, obviously this tree is equivalent to a tree like this. I take this and I put it on top here. And so they say, well, you should start out by splitting halfway. So you take N1 up to whatever, the other on the right side, because then with the randomized methods, a low rank approximation is actually more efficient than if you would separate a small one out.
Why would it be more efficient?
Because then let's say every N1 up to ND would be the same, just N. You would have an ND half matrix by ND half matrix. So the complexity of the randomized methods would be about ND half.
Yes.
Is there an opportunity to consider this in your setting as well?
Okay,
Because
so actually, I don't know the paper you're referring to, but I remember a paper like 5 years ago with a very good title. It was called Square Deal.
Yes.
And it made the same observation, and they made a big statement that they could reduce the complexity. And indeed, I mean, it's an exponential improvement of the complexity if you divide it by 2, the factor, the power. But what you get here, of course, is the H Tucker way, the hierarchical Tucker representation of a TT, and it's known that hierarchical Tucker has better complexity than TT because of the logarithmic tree. The depth is logarithmic, so it's not a big surprise. Okay, you can work everything out and do the complexity and then say that the statement is better. Sure, but for us, I don't think for us this would be beneficial because again we don't have the sequential nature. I don't know. It's an interesting question, but for the moment I don't see at all how it applies because we do all the flattenings, right, from 1 to D.
Yes.
And we have one that's in the middle.
Yeah.
We also have one that's completely unbalanced from the left and from the right. So, and we need the very unbalanced ones as well. We cannot avoid that. We cannot only do it in the middle. But maybe you can cut it and do things like recursively. This would be maybe, maybe that's an interesting thing to work on.
I don't know how many years Rick still has left in the PhD.
0.4.
0.4. No, that's gonna be a nice exercise.
Yes. You can do it as a master thesis.
No, I mean,
No. That's all your students, not you.
Okay. We'll think about it.
Because I think if I recall correctly, there's also a streaming version of the SDH with the algorithm. So I thought, if I recall correct, it was somehow possible.
Really? Okay, that would surprise me. Are you streaming?
Yes, exactly. But it was
But streaming is used in many different ways. So when we wrote the paper, I actually dug in the literature a little bit, and streaming is not some definition that's very clear. So you should say one pass. One pass, and so because streamable, okay, you can update and you can do many things, but it's like one pass is like more interesting.
I think the paper we looked at, so it was not from the review, right?
Could be.
That was about where you have some data set and you keep adding slices to it.
Okay. That's different.
Yes. But that's quite obvious how to do that. I'm thinking of a different paper.
Yeah, this is linear updating. It's not adding slices, not adding columns to a matrix.
Yes and no. I guess that you can extend it to the.
Yeah, you can add zeros in there and then add it with. Okay, this you can do, but I'm not sure this will bring anything. Maybe we're good. Another masterpiece.
Or maybe a bachelor thesis that one.
Good luck finding a student.
Right. All right, any other questions? If not, then we can, there's no one online for a question, then we can thank Bart again, of course. And now we should have some time for some coffee break and some socializing.
Back at 45.
Sorry?
We're gonna be back at 45.
Yes, I think we're back at 45. All right.
There's somebody talking from Bologna.
Yeah.
Yeah, I'm sorry. I have to go.
No
I have
problem.
to,
Yeah. I mean, we knew about it already.
Yeah, that's a
Well, thank you for being here. Always a pleasure.
I'll take some water and then I'll go.
Yeah, great. Or coffee or cookies, take some for the road.
Get
Ja, goede vraag.
Ik heb het gewoon ik heb hem natuurlijk gewoon online, hè, dus misschien ook wel.
Kun je misschien al gewoon doorsturen, dan kan ik iets horen bij Marco, wat we dan moeten doen. Maar ik denk waarschijnlijk is dat gewoon doorsturen, die ticket.
Ja, ik weet gewoon, vorige keer was het ingewikkeld, want ik moet in het systeem. Ik weet niet, het is al even geleden, maar vorige keer was het misschien misschien zit er nog het systeem. Ja. Maar mijn adres is oké, ik zal het gewoon doorsturen, maar gewoon.
Ja, ik kan dan niet horen, dan wat we wel zeggen wat er is gebeurd, dat ik niet zeker zou horen. Mag ik nog iets zeggen?
Ja,
Our side here.
Emanuele, vuoi provare intanto a condividere le slide?
Stel dat je uiteindelijk eigenlijk een video.
Ciao Davide.
Ciao.
En dan op die manier kan je.
Ah, ma tu sei lì proprio in...
Sì, sì.
Ah. In dipartimento non c'è una connessione, sono dovuto tornare a casa.
Hai fatto bene.
Allora,
In principe moet je herkennen. Jij moet het aanpassen.
Perfetto.
sei?
Sì. Va bene, allora 5 minuti e ripartiamo.
Ok.
Ok, grazie.